continue. So let me make a remark. Basically, once we have all this functional framework, very big, for sure, we have a sequence of steps that we might follow, let's say. First, we have to establish uniform bounds. After establishing these uniform bounds, we can find limit functions and its identification. And basically, finally, determine the limit problem. Basically, these few steps here is a must-do, usually independent of the method actually you use. The uniform bound is the very first step for homogenization problems, asymptotic analysis problems. As well, to determine limit functions and so on. So let's just start the proof. So first, recall that a solution of our reaction diffusion problem is a weak solution of the following problem. Phi for all phi in H1. And it's very simple. You just, to verify uniqueness, the existence and uniqueness of solution, you just apply the Lex mugram for existence and uniqueness, apply the Lex mugram. I don't know if it's like this that we write it, but anyway. Theorem. So it's very simple. For each epsilon, we have a unique solution, and we have no problem here. So let's first prove the uniform bounds. So let me call this variational formulation star for the moment. Take as a test function the own solution in the variational formulation star, and we get that plus this, and we use Holder inequality here, which will lead us to this. Okay. And finally, multiply by 1 over epsilon, and then we get here we will have the W1P norm corrected. That's why the 3 brackets of H1 squared, it's less or equal to. So the 1 over epsilon we spread for both, And so we have the three brackets here, as well here. But, of course, it's very easy to see that the L2 norm is less or equal to the H1 norm, okay? So we can go further in the inequality here, and then we can put the H1 as well here. And we simply simplify here, and we can conclude that it's less or equal to the triple norm of F epsilon here in H1. And by hypothesis, this is less or equal to a constant that depends on epsilon, and we have proved the uniform bounds. Very simple, very fast, no difficulty. So it's okay. Now we can apply the previous theorem, theorem 7. There is some space. The limit of bounded solutions. So, by theorem 7, there are U in H1 of 0, 1 and U1 in L2 of 0, 1, 2 values in H1. So recall that this symbol here means periodicity in the variable y1. Such that the unfolded solution converges strongly to U in L2 of 0, 1, 2 values in H1, and that the unfolded gradient converges weakly to U of x. Weakly in L2 times y star. So, with the convergence in hand, now we just have to rewrite this variational formulation. So, next we unfold the expression star and get now we can rewrite this as the unfolded variational formulation. Notice that there would be a 1 over L here and here, but we can drop because there is on both sides, so there is no problem for any phi in H1 of R epsilon. But to pass to the limit, we have to consider test functions depending only on the horizontal variable. So take phi in H1 of 0, 1. And so I will call this expression 2 stars. And pass to the limit in 2 stars. We have, just applying these previous convergences, we simply have the following. So, since the test functions just depend on the first variable, on x, you have to agree that this term here will multiply by 0, okay, because the derivative in this of a function like this in y will be 0. So what we will have is basically this. Plus the u by the phi equals to f hat by phi. So we almost have our limit problem. What we need to do next is to identify this u1 function, okay? So I put 2, okay. Now let's say we have this item 2 prime. So we next identify u1. For this, we basically use the Tortoise oscillating test function, which is simplified with the unfolding method. It's an important remark. So to use this Tortoise oscillating test function, we get, let this function phi be a C0 infinity function of 0, 1, and psi be a H1 periodic function of the cell. We define epsilon phi here. So, since this psi is periodic, we extend it in the horizontal direction, and then we can take this division by epsilon both in the first entry here and in the second entry of psi, so this function is well defined. And now notice that if we get this phi epsilon and derivate in x, which will be the variables of r epsilon, we have, here, let me make a small remark. I will simplify the notation just calling this by psi epsilon, okay? When we have this division by epsilon inside its coordinate, and so apply a simple derivative, we have this, and then we apply, we derivate it and multiply by the remaining. So 1 over epsilon will go out, will cancel with this one, and so we will have this. Recall that the variables of psi are y1 and y2. We have this derivative, and then we derivate in the second variable, and so we will have this here, okay? And so, notice that this happens, and if we unfold each one, what happens? If we unfold this first one, we will have the following. So, recall that when we unfold a function like this, with entries like this and being periodic, when we apply the unfolding, we just have the psi in these original variables, okay? So I will write it like this. Of course, this will have basically everything, but, and so. Okay? And of course, if we apply the unfolding in the second, we will have this, and the psi, the derivative in the second variable, and like this. And once we pass to the limit in each one, which means that if we pass to the limit in the gradient of phi, we actually have, so first, this little phi basically is a C0 infinity function. So it converges when you apply the unfolding like this. It converges strongly to itself. It's proposition 5, if I'm not wrong, of convergences. This will be fixed due to the unfolding properties. And so what will happen? This will go to 0. This will go to phi. This also goes to phi. And we have the gradient on the y variables of psi. And this convergence is strongly on LP of 0 on times y star. So once we establish, oh, there it is, okay. These convergence properties, now we get, now take this phi epsilon as test function in two stars. I remark that if I apply the unfolding directly on the phi epsilon, it will converge to 0, okay? So we will have the gradient of phi epsilon plus so notice that this will converge to 0. Look here that the epsilon remains. This also converges to 0, the same thing. We have an epsilon here and something that converges, okay? These two terms will go to 0. This will converge to the following. Here I just dropped a little bit the domain, okay? So we have the UX. So here we just take this convergence below. We will have the phi, the gradient of psi here, which will be equal to 0. So this, if you recall, for you who knows a little bit of homogenization, this is the corrector equation somehow. Of course, we have to make it a little better, but first, since this phi is any function in C0 infinity, we can rewrite this above relation like this, okay? Just in y star, 0, almost everywhere, for almost every x in 0, 1, okay? So, in order to see that this has a unique solution, we have to consider the quotient space H1 here R. Why? Because we want to determine a unique U1 function that satisfies. If we don't have this, what it would mean? That if this one is a solution, then this plus a constant also would be a solution. And so we need this quotient with R in order to exclude these quotients. So we will have unique solutions for this problem. So consider this, then this auxiliary problem, let's say prime, then auxiliary problem prime has a unique solution for almost every x in 0, 1. Moreover, I erased already, okay. Recall the auxiliary problem we had in the statement of our theorem that let me change the test function a little bit. So compare this with this. Notice that if we multiply this by minus ux, so we can, because this just depends on x, okay? This doesn't depend on the variables that are in the problem. If we multiply this by ux, then what happens? We immediately have, we immediately have that the gradient in y of u1 is exactly equal to dx, okay? Do you agree? Because we multiply by minus x, put it in the left-hand side, and then we can rewrite it as the same, since this has a unique solution. And this has as well. And of course, we are quotiating it. The gradient then is okay to rewrite it like this. Of course, this is a little bit formal, this what I wrote here, but it's a kind of justification. So this is equal almost everywhere in here. So if we take so next to recall the almost limit problem that I shouldn't erase below here, but anyway. Which is this. So, of course, the first variable of here, the first entry of the gradient is equal to the first entry of here. Then we can change this here by, okay, plus. Notice that both functions does not depend on the variables of y star. Then we can put the measure of y star outside, and we have u phi. Here with f we can do somehow the same, say like this. The variables of Okay. And then now we put it this integral between 0, 1, integral in y star of 1 minus the derivative of x here, dy, by the ux phi x plus, so okay, we just take in evidence the ux here, put it outside as well the phi, and so we divide everything here by y star, and we divide it by y star, okay, this expression. And so we will have this equals to u phi to 0, 1 of a bar f and here. So if we call this coefficient here q, we will have the following. So we will have the integral over 0, 1 of q ux phi x plus u phi 0, 1 f bar phi, where q is this, f bar is this, and we have the result. So one important remark that should be stated is that if we get so a remark, a last remark from from this 3 star here, we get that is equal to oh yeah, is equal to this is equal to this, and the and this q which is this can be rewritten as this minus minus this, and this should be bigger than 0. I guess I am doing some mistake here. This coefficient is bigger than 0. What's the mistake I'm doing here? Oh, okay. Okay, this should be bigger than 0. What am I doing wrong? This q should be bigger than 0. Oh, okay. 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 It's apply a Holder inequality here, and then we will have this in L2, and then the gradient here is less or equal to this. Okay. And so if we get the Q, which is this, yeah, okay. This is equal to 1 minus this. And we can reverse. Oh yes, it was the contrary, yeah. Which is bigger or equal to 1 minus here, okay. 1 minus, we reverse, so we will have this. Here is 1/2. Oh, then it's okay. Okay. And then it's positive. And then okay. Yeah, okay. And then this is positive because the measure y star is equal to this, and this is equal to 0L, 0G, y2 dy1, and this is equal to 0L of G dy1. This is bigger than L by G0 because G0 is the minima of G. This is positive. On the other hand, this is also smaller to L, and this is also positive. So the 1 over y star will be less or equal to this. So LD0 over 1/2, and yeah. Sorry? Oh, yeah. And this is true. And what am I doing wrong? Because this should be very easy. I guess I'm taking the wrong approach. So anyway, you can see in the reference, I will put that there later, that this is true, and if I'm not wrong, this is less than 1. I'll go through the reference again, and I will mark it in the next lecture. I have to re-see this part. But actually, if I'm not wrong, it's something like this. this coefficient is between 0 and 1. So being this the case, this has a unique solution, and there's no problem. It's something very stupid that I'm not seeing. So next time I will do it again and prove the case smaller than 1, probably the bigger than 1, the strongly oscillating boundary. And then in the other, I will do some remarks for the Stokes equation.
Okay, so you'll have 2 more lectures.
Yes, so 2 more lectures.
I'll write an email that we can break, and then we will continue.
Okay, perfect. So see you next time.